I'm really honored to be here, and I'm deeply impressed by the number and the quality of people here. There are, I'm told, 700 people here. So if the United States is 50 times larger than us, then in each of one of their meetings, they should have 3,500 or 35,000 rather, order of magnitude. And they don't. So this is really an amazing event, and I really appreciate the invitation and, of course, the honor of receiving the medal. Let me now go to my talks. Usually I hate to be restricted to one point in space. I usually walk, but this time I will talk to the microphone. So the subject is the discovery of quasi-periodic materials. I will tell you the story. Wonderful. I will tell you the story of the discovery and what followed after the discovery. That is, if I can find how to shift gears here. Yes. Okay, I did. So, the period is the mid-80s of the previous century. And in the mid-80s, there were 3 surprising discoveries on the structure of matter and its properties. Now, the first discovery, chronologically, was 1984. Actually, the discovery was made in 1982, but 1984, the announcement came, and this is the discovery of quasi-periodic crystals, and the names of Ilan Blech, Denis Gartas, and John Kahn joined my name on this discovery, or this announcement. Then came Fullerene, 1985, and then came high-temperature superconductivity. Year after year, all these 3 discoveries received the Nobel Prize, as well as many other recognitions. Now, let's talk a little bit about them. Let's talk first about high-temperature superconductivity. Superconductivity, as you know, was discovered at the beginning of the last century, and it was an amazing discovery, but it was thought and proven that high-temperature superconductivity will not exist at temperatures higher than, say, 30 degrees K. And so when the discovery of high-temperature superconductivity that shifted from liquid helium to liquid nitrogen, which is a very important shift in terms of applications, everybody was elated and happy, but nobody objected, because here it is. When fullerenes were discovered, again, this is another way in which carbon atoms can shape, and nobody objected that. Wonderful. And then nanotubes came, and recently, last year, Nobel in physics, of good friend, and so. But when quasi-periodic crystals were announced in 1984, they met with great opposition. And the reason is that it contradicted the basic laws of crystallography. When the announcement came, immediately people joined force and started to study, and I will tell you, but in the period between 1982 and 1984, the opposition was fierce, as I will describe later. So in order for you to understand, I'm talking to the students now, of course, to understand what I'm talking about, let's talk a little bit about order in crystals, periodicity, and rotational symmetry. So let's say that we have a structure here which is ordered. Clearly, there is order here. And in each and every direction that you look, there is also periodicity. So if you look along this line, there is periodicity. If you walk along this line, there is periodicity. Anytime you join 2 atoms, you join an infinite number of atoms, and there is periodicity in each and every direction. So when I talk about periodicity, this is it. Let's talk a little bit about rotational symmetry. We have a grid here, which we can rotate, and in order for you to know that I rotated it, I added a handle. The red handle at the top will tell you how I rotated it. So Here we go, 90 degrees, 180 degrees, 270, and back to where we were before. And so this structure has a fourfold rotational symmetry. And let me show you some other examples of rotational symmetry. The definition, by the way, of rotational symmetry, an image has a rotational symmetry if there is a center point around which the object is turned a certain number of degrees, and the object still looks the same. That is, it matches itself a number of times, it is being rotated. So this is rotational symmetry. And here are examples, twofold here, threefold, oops, back, yes, fivefold, and sixfold here, and you can continue. This is a rotational symmetry of a motif of one molecule in a structure. Now, let's say a few words about the science of crystallography. This year, we celebrate 100 years to the famous experiment of von Laue, in which he showed in one experiment that X-rays have a wavy nature, and also that atoms are arranged in the way people thought before they are arranged. And by this, he opened the field of crystallography. A year later, the Bragg family turned the experiments of von Laue into a science, and this is why the next year is going to be the International Year of Crystallography, except for the little fact that they don't have enough money, so they postponed it for 1 year. Hey, that's a fact. Okay, so this was the year in which crystallography started. And let me tell you something about what happened that year. You see, the crystallographers before that year were the geologists who found crystals, and the crystal had facets, and they measured the angles between facets and deduced structures or atomic structures according to the angles between the facets. But they did not have a positive proof that what they are saying is correct. And so when X-ray diffraction was invented, or discovered, if you will, a new community of crystallographers was born, and they said, we are X-ray crystallographers. We are not those primitive geologists with those facets. We have a scientific tool. And we are the X-ray crystallographers. By doing so, by distinguishing themselves from these people, the geologists, and by declaring themselves as X-ray crystallographers, limiting themselves to X-ray crystallography, they also limited themselves from electron crystallography, from electron diffraction. They did not believe in electron diffraction. They limited themselves, and that's bad. Okay, so all the crystals that were studied from von Laue on for 70 years had one thing in common. Of course, they were ordered. That's the definition of a crystal. But they were also periodic. All of them were periodic. And so a paradigm was born that a crystal, and this was also a definition, a crystal is ordered and periodic. No exception. And indeed, for 70 years, hundreds of thousands of crystals were studied. So why would you expect anything different to happen? And the science of crystallography was what we call a mature science. Mature science is a science in which you don't expect anything new to happen. Yes, crystals, new crystals were discovered, but each one of them had a drawer. So if you discovered a crystal with DO19 structure, oh, welcome to the drawer, and this is crystal number 2084, welcome. So there were drawers, but nothing new to be discovered as they thought. And based on that, definitions were stated. And this is from a book of X-ray crystallography by Quality. I studied this book when I was young. And a crystal is a solid composed of atoms arranged in a pattern periodic in 3 dimensions. Very simple definition, very clear, no question asked. Another definition, which is just about the same, in different words, this is from the book of Barton Masalski, Structure of Metals, And it says atoms in the crystals are arranged in a pattern that repeats itself in 3 dimensions throughout the interior of the crystal. The same definition. A crystal is ordered and periodic, period. And then the crystallography those years was also described in books. This is a book by Kittel, and I marked here, I know you cannot read it, and so this is why I magnified it. And it says the following. We can make a crystal for molecules which individually have 5-fold rotation axis. 5-fold rotation axis. But we should not expect the lattice to have 5-fold rotation. Why 5-fold rotation is forbidden? Because from the mathematical aspect, if you have an ordered and periodic structure, then the only allowed rotational symmetry in that structure are 1, 2, 3, 4, and 6, no 5, and nothing beyond 6. These were the rules, and examples are given here. This is an electron microscope picture, just high magnification image, phase contrast of atoms in diamond. It is a periodic structure, and you can see clearly if each white point is an atom, you can clearly see that there is order and there is periodicity. Very simple. Actually boring. So this is atoms in diamond. Now, let's talk about the diffraction pattern. The diffraction pattern from a periodic crystal has the same characteristics. This is the reciprocal space. The crystal exists in the real space. This is the reciprocal space. This is the space in which the diffraction points exist. It's a space, 3-dimensional space. And what you see here, these are not atoms. These are diffraction spots, electron diffraction spot. And what you see here is that clearly, this is a transmitted beam right here. Each one of the other beams are diffracted. And what you see here, that as well as in the real space, there is order and there is periodicity also in the space of the diffraction in the reciprocal space. And so the rules that exist in the real space also exist in the reciprocal space. There is periodicity. The rotational symmetries that are allowed are 1, 2, 3, 4, 6, no 5, and nothing beyond 6. And then something happened, really shocking for the community of crystallography. And that something was a new definition for a crystal. And that definition we have to study because it's a wonderful definition, and I will tell you why.